So today we're talking about relative atomic mass. Relative atomic mass is the way that we find the masses, or other scientists have found the masses, of various elements. Elements are too small to weigh, or atoms are too small to weigh individually. So we compare them all to one element whose mass has been defined. But before we do that, let's take a look at using this with people. Now, suppose people couldn't be measured on a scale. I know, just go with the story. So let's define a standard person as 150 pounds. Like when you get in an elevator and you see how many people it can hold, and they figure a standard person weighs like 250 pounds. When you look at one of those certificates that you probably never looked at. Okay, so anyway, our standard person is 150 pounds. And if we look at other people relative to the standard person, we find that a 300-pound football player is 2 standard people, because 300 divided by 150 is 2. If we have a 75-pound child, that 75-pound child is a half of a standard person, because 75 divided by 150 is a half. Lastly, a 15-pound baby is 1/10 of a standard person using the same method. Okay, so what I've done is I've defined a standard person, and so if that's one standard person, we can see a football player's mass is 2 standard people, a child's mass is a half a standard person, and a baby or toddler's mass is a 1/10 a standard person. So these are units that we have defined relative to an arbitrary person that we've decided is the standard person. So what scientists have done is they have, well, first of all, atoms are too small to weigh. That should be 2, T-O-O, on a scale. You know, they're around 2.66 or 3 times 10 to the minus 23rd grams. So all their masses are defined relative to one isotope of carbon, and that is carbon-12. We talked about the hyphen notation before. We write the name of the element, then hyphen 12, and 12 is the mass number. It's the same as writing a C and a 12 together. If you wonder why you're seeing all the red stuff that I should have filled in, like as I was doing this, it's because I made this giant mistake, and this is the second time we're doing this one. Okay, so carbon-12 was our standard element, and one atom of carbon-12 is defined as having a mass of exactly 12 atomic mass units, which is written most times as 12 AMU or 12 AMU lowercase. The general chemistry book writes 12U. I have never seen that before. I'm always going to use AMU. But carbon-12 is the element for which everything, to which everything is compared. So an example, an atom of hydrogen 1, regular hydrogen with no neutrons, is 8.4% the mass of carbon-12. All right, so it's less than 1/10 the mass of carbon-12. What is the mass of a hydrogen atom in atomic mass units? Well, we take 12 AMU, the mass that we're comparing it to, and we multiply by the fractional form of 8.4%. All right, we can't have it multiplied by 8.4 because that would make it heavier than carbon-12, and it's less than 1/10 the mass. So you divide this by 100 to get 0.84, which is the fraction, or it's what I'm going to call a fraction. So 12 AMU times 0.084, yeah, this is where the mistake was, ends up giving you a mass of 1.008 AMU. And then all of the other masses of all the other elements are done the same way, all relative to carbon-12. Oxygen 16 used to be the standard, but they switched to carbon 12, oh, I don't know, 50 years ago or something. And that's what we now use.